So what we have here is a strain rosette problem. It's saying that the structure is made of ASSI 302 stainless steel, and the following gauge A, B, and C right here is given to be out to these values. So these are our given values. So the problem give us the strain gauge value, and it's asked to determine the principal stresses and the principal shear stress. So in order to get from the strain gauge to principal stress, let's refer to this diagram right here. So from these strain gauges, what we can find out of it using the relationship is with strain gauge and state of strain. So from strain gauges, we can get the state of strain, and from there we have two options in order to get to to find our principal stresses and principal shear stress. We can find the state of stress first, or the principal strains first, and then after that you can find a principal stress. But in our problem, it's specific as for stress from for stress from transformation uses more circles. So because of that, we're gonna use this left path to find our principal stress. And in order to find what's given to it is the strain gauges, and we can do that by using the strain rosette equation right here. So after that, we'll be able to obtain our state of strain, and after we get our state of strain, we're gonna use Hooke's law. Because Hooke's law describes the relationship between state of strain and state of stress. And after that, we're gonna use more circles to find the principal stress out of state of stress. Here we go. So what's given to us is sigma A equal to, so this is our given values, and our governing equation that ties the relationship between strain gauges and state of strains is this. So I already wrote it up here. So in the place of n, you can plug in A, B, C, or D. So if this is to say sigma A, it'll be sigma A and then theta A. So all the n's could be any given values. So for our first one, we would have sigma A is equal to sigma A cosine theta A plus epsilon y sine square theta A plus gamma xy sine theta A, and then this is time cosine theta A. So we give what was given to us is the values and also the angle of each strain gauge. So for theta A, it's actually equal to 0 because it's located on the axis. And for theta B, it's 60 degrees on here, but however, when we measure the angle of the strain gauges, it's from the positive y-axis. So so counterclockwise would be positive, so clockwise would be negative. So our theta B would be negative 60 degree, and our theta C is just negative 120 degree. So now we have what we need. We have sigma A. There should be epsilon. So we have epsilon A, and what we're trying to find is to find the state of strain. They are just what they are essentially is just, so I'm gonna write here, find state of strain. That just basically find epsilon x, epsilon y, and gamma xy. That's essentially what we're trying to find. So we have three equations. We would have three equations if we plug all this into here, and we would have three. Yeah, we have three unknowns. So it's a doable equation. Just to check if it's solvable or not. So for the first one, we have. Let's see. I'm just gonna write right here. So it would be sigma. So it'd be. So sigma A was given, so it's be 475 micro inches per inch equal to, epsilon A was given, so epsilon x cosine square 0 plus epsilon y sine square 0, that is just 0, and plus gamma xy sine 0 cosine 0. So sine 0 is just 0, so these are all go to 0, so then we would just have, so and then cosine square 0 is just 1, so we have epsilon x is equal to 475 micro inch per inch. So we found one value already, and the same thing for epsilon y. You just plug in y for all the n terms right here. You just plug in y for all the n terms right here, so you have epsilon b equal epsilon, sorry, it should be x right here. So this is epsilon x cosine theta b plus epsilon y sine squared theta b plus gamma xy sine theta b cosine theta b. So epsilon b was given as 200 micro inch per inch is equal to epsilon x is also given. We already found epsilon x, so epsilon x, which is, I'm just gonna write it like this, cosine squared, and the angle was said to be negative 60 degrees. Plus epsilon y sine squared of negative 60 degree plus gamma xy sine of negative 60 degree cosine of negative 60 degree. And you just plug in, so we have like this 200 micro inch per inch minus 465, so this minus micro inch per inch cosine squared negative 60 degree equal to, I just basically move this side, subtract this side to get to this side, because we already know our epsilon x value, and then sine squared negative 60 is just 0.75 epsilon y plus, and then sine negative 60 and cosine negative 60, if you plug into that calculator, it would come out to be 0.43301 gamma xy. And when we saw the left side, we would have 81.25 micro inch per inch equal 0.75 epsilon y plus 0.43301 gamma xy. So we'll say that's our equation 1. And then for strain gauge C, so epsilon C is equal to the same thing. You just plug in C terms for all the n right here. So 1, yeah. And then epsilon x cosine squared theta C plus epsilon y plus, plus epsilon y sine squared theta C plus gamma xy sine theta C cosine theta C. So we have, so we already know our epsilon x value, so I'm just going to move to the left side like how I did last time, and epsilon C is negative 250 micro inch per inch minus 475 cosine square of negative 120. Yeah, so because we said right here is negative 120 degrees, and then equal sigma, epsilon y sine squared negative 120 plus gamma xy sine of negative 120 and cosine of negative 120. And this is just plug into the calculator. So when you solve for the left side, you get negative. Yeah, when you solve for the left side, you get negative 368.75 microinch per inch equal to 0.75 epsilon y plus gamma 0 plus 0. This should be negative. Sorry, because the angle that come out of that should be negative, and because this angle and the angle come out, it should be positive, because when you do sine negative 60 and cosine negative, it should be negative. So this is actually negative, and this is positive right here. So this is gamma xy, so, and then this would be 0.43301 gamma xy. This is positive. Yes, positive. So let's call this our equation 2. So right now we have two unknown, epsilon y and gamma xy, but we have two equations for that. So we can just add the equation together, and so we'll have 81.25 microinch per inch equal to 0.75 epsilon y minus 0.43301 gamma xy. So this obviously go to 0 because it's just the opposite of each other. So we have 0 gamma xy. And when you solve this, it comes out to be negative 287.5 microinch per inch equal to 1.5 epsilon y. So you just divide 1.5 over here, and we know epsilon y is equal to negative 191.667 microinch per inch. So we found our stress, a strain y to be this much. And after that, you can just plug into one of these equation 1 or 2. So we can just plug into the first one to find out gamma xy. Let me move this up a little bit. So we have 81.25 microinch per inch equal to 0.75 minus epsilon y, and epsilon y is just negative 191.667 microinch per inch minus 0.3301 gamma xy. So after you just do some rearrangement, so you subtract this over here, and then you divide it by negative 0.44301. So gamma xy turn out to be negative 519.828 microinch per inch. So we found our state of strain. Epsilon x right here, epsilon y, and gamma. So if you refer back, so we found our state of strain right here. So we found our epsilon x, epsilon y, and gamma xy. So check. And then the next step that we need to do is we need to find the state of stress. And to do that, which is essentially just sigma x, sigma y, and tau xy. That's basically what state of stresses are. And the relationship that governs relates the two between the state of stress and the state of strain is Hooke's law. So I have this is an equation for Hooke's law that we'll be using, generalize Hooke's law. So yeah, to find, so right now we'll have to find sigma x, sigma y, and tau xy. So sigma x is equal to E, the modulus of elasticity or Young modulus, over 1 minus Poisson ratio, sigma x, plus Poisson ratio, plus Poisson epsilon y. Sorry, I keep saying sigma x, but it's actually epsilon. And then the sigma y is the same thing, just reverse it. So epsilon, the Young modulus, 1 minus Poisson ratio, epsilon y plus Poisson ratio times epsilon x. And then the shear xy is just the modulus of rigidity times gamma xy. Just want to make sure that's correct. Yeah. So this is the Hooke laws that we're using, and obviously we need to know some properties constant that relates to our stainless steel. So the problem gives us stainless AISI 302, and we need to find the modulus of rigidity as well as the Young modulus for that specific property. So E is equal to, so if you look over here, stainless steel bar of AI is 302, and if you go over here, the Young modulus, it doesn't matter for cold roll or annealed, it's the same. So for the Young modulus, it's equal to 28 times 10 to the 6 psi, or, and since the problem asking us in the KSI, we just convert it to a KSI right now, so it's just easier. So that would be 28,000 KSI, and G is equal to 10.8 times 10 to the 6, that is just 10,800 KSI. And Poisson ratio can be found to negative sigma y over sigma x. And it's just good to write what our values were before. So, and sigma x that we found was 175 microinch per inch, and sigma y what is negative 181.667 microinch per inch, and gamma xy is 591.82 microinch per inch. Yeah, that's correct. So our Poisson ratio is just equal to negative 191.667 microinch per inch divided by 475 microinch per inch, and that's equal to 0.4035. That's our Poisson ratio. So this is the matter of just plug and check into the Hooke's law right now, because we have all what we need. So sigma x is equal to 28,000 divided by 1 minus 0. I'm missing something here. I think this is supposed to be squared. Yeah, it is squared. Okay. Yeah, that's supposed to be squared. So 0.4035 squared times epsilon y, which is negative 191.667. It's in microinch, so I'm just going to convert it to inch. Negative 6 times to negative 6 plus Poisson ratio 4035 times epsilon. Sorry. Yeah, this should be epsilon x. So this would be 475 times 10 to the negative 6. Yeah, this should be epsilon x, yes. Epsilon x plus Poisson ratio, and then times epsilon y. Epsilon y, which is negative 191.667 times 10 to the negative 6. So after you plug that into the calculator, so sigma x came out to be 13.3 KSI. So we found sigma x. And sigma y is just equal to E over 1 Poisson ratio squared, and epsilon y plus Poisson ratio epsilon x, and that which is equal to the same thing, 28 minus 1 minus 0.435 squared. Epsilon y is negative 191.667 times 10 to the negative 6 inch per inch plus 0.4035 times 475 times 10 to the negative 6 inch per inch. Yeah. So a sigma y is equal to very small number, 1.505 times 10 to the negative 4 KSI, or I like to write it as 0.000150 KSI. Just keep it consistent with sigma x. And our tau xy is equal to the modulus of rigidity times gamma xy, and we found it to be for our stainless steel, 10,800 KSI times gamma xy found to be negative 519.82 H times 10 to the negative 6 inch per inch, and that's turned out to be negative 5.6147 KSI. So we have found our state of stress with the corresponding strain gauge that was given from the original problem. And to find the principal stress and the principal shear stress, we need to use Mohr circle. According to our problem, we can do it another way by using an equation that converts, that do stress transformation. But for our problem, we need to use Mohr circle. Yeah. So let's see. So this is to find principal stresses, yeah. Basically just sigma 1, sigma 2, and tau max. Yeah, so I like to draw a little diagram to just demonstrate what we're doing. So here, then this is the steel structure, and what given to us is sigma x. So the stress in the x direction is 13.3 KSI, and the stress in the y direction is, I believe this is supposed to be negative. Yeah, this is negative. This has to be negative. Yeah, because, yeah, it's supposed to be negative. So negative 0.0001505 KSI, very small. And the shear stress is negative 5.6147 KSI. So if you can put into this little diagram what essentially what it looks like, the stress in the x direction, so this is sigma x, and then this is negative sigma y, and tau, since this is negative, think of it like a negative slope, So it would have a direction of like this. So this is like a negative slope right there. Yeah. To construct a Mohr circle to find the principal stresses, we need to plot. So plot sigma x negative tau xy and sigma y tau xy. Yeah, positive tau xy. So we just need to follow this, and then we'll go from there. Let's see. All right, so this is our circle right here. It's a circle. So plot sigma x tau negative tau xy. So that's essentially 13.3 KSI. And negative tau xy, tau xy is negative 5, so it just becomes positive 0.6147. And then this one would be negative 0.001505. And negative 6.147. Okay, so this one, so plot 13.3, and so we said 13.3 will be right here. No, just an estimate. 13.3, and this is 5.6147. So that's our first point, and our second point would be negative 0.000150, and this is negative 5.6147. So it'll be right there, and you just connect the dot. I like to find the center, so I would know like where the top of the circle will be. So the center, it's just the average between the two. So the average stress is the center is 13.3 plus 0.000150 divided by 2, and we have 6.649923. Okay, so this is the center. So that's 6.64499923. Okay, so this is center, so our circle will look something like this. Circle will look something like this. Okay, and our radius, so this is our radius r, we can essentially find using Pythagorean theorem. So we need to find the distant A and distant B. So distant B is just our tau xy, just this distance right here. So our radius is just equal to, so the distance between these two is just 13.3 subtract the center, 6.64999923 squared plus tau xy negative 0.6147 squared. So the radius turns out to be 8.703 KSI. So we know the radius is equal to this much. And according to Mohr's circle, this is going to be our sigma 1, and this is going to be our sigma 2. And our tau xy is equal to, so sorry, our tau max is equal to the radius. So this is our tau max right here. You can essentially just look at the shift right here. It will go right here, but it's the same thing. So to find sigma 1, it's just equal to, what I like to do is, sigma 1 is just equal to the center minus the radius. So you put the radius over here, it would just be this distance right there. So the center minus the radius, plus the radius, sorry, sigma 1 is supposed to be positive, so plus the radius, so the center is 6.64499923 plus the radius is 8.703 KSI equal to 15.345 KSI. And sigma 2 is just the opposite one. It's on the other side, so it's just minus the radius. Center minus radius is 6.649923 minus 8.703 KSI. It just comes out to be negative 2.061 KSI. And if you were to like check, based on what I said earlier, if the end on the axis, on the x-axis, the end of the circle is sigma 1 and sigma 2, and if you check out value, this is our point here, 13.3, and so sigma 1 should be greater than should be greater than 13.3, and sigma 2 should be less than what we found for to be less than sigma y, and it is. So these two values are reasonable. And tau xy, tau xy is the radius of Mohr's circle, so it just be 8.703 KSI. So we have found sigma 1, the principal stress, and the maximum principal shear stress. I just want to, thank you for watching the video, and one last thing, I need to sign this. So that's my signature, and here's a verification of proof that I did the video. Thank you very much for watching.